right, welcome everyone to this video where we will be solving exponential equations. All right, when we say solve, again, we're looking for the value of whatever variable is given. So on the left side, we will be looking for the value of x, and in the right side example, we will be looking for the value of a. We talked about two different cases when solving exponential equations. The first case is that I can change base. All right, so I'll write that down here. The first case is I can change bases. The second case is using log to solve for whatever variable you're given. So the left side is a case of changing the base. The right side is a case of using log. Let's get into this left side example first. We're given 3 to the x minus 2 equals 27 raised to the 3x plus 1. So here's the idea of changing base to where we talked about that property of equality of exponential equations. That's a long definition that we read about, the key idea in the last class, where it's like, okay, b to the x equals b to the y. In this game of placement, if b equals b, then that means these exponents must equal each other as well. X must equal y. So that idea of, hey, same base means equal exponents. Okay, we're going to use that to our advantage here on this left side example, and I'll label this number 1 and number 2 so I don't get confused. All right, so 3 to the x minus 2 equals 27 to the 3x plus 1. Clearly, I don't have the same base. My base on the right side is 3. My base on the left side, the left side is 3. My base on the right side is 27. Not the same number at all. But because we're such powerful mathematicians, we do have the power to change any base we want to have common or like bases. What's the definition of a common or like base? It's just a base that's the same. All right. So in this example up here, these are common bases because they're both b. These are not common bases because one is 3, one is 27. So I want to change them to both be the same number, common base. The only one I need to change here is 27. I can make 27 look like 3 raised to the something, a base of 3. Right now, the left side's base is 3. We're going to keep that the same, and we're not going to change it. So matter of fact, I'm going to bring down 3 to the x minus 2. I don't want to change the left side at all. But I do want to change this 27 to look like 3 raised to the something in order to create a like base with my left side. So let's think about that mental math. 27 equals 3 raised to the something. You can do this with guessing, checking your calculator. You can do this with mental math if you just know the answer right off the top of your head. Or think about an exponent means how many times can I multiply 3 by itself to get 27? Let's see. 3 times 3 equals 9. Times another 3 equals 27. So that lets me know that 27 really equals 3 to the third power because it took 3 times for me to multiply 3 by itself to get 27. So this knowledge is going to help me put into my equation to replace what 27 used to be now with 3 cubed. Again, because I just solved down here in this highlighted portion, I know that the true statement is that 27 does in fact equal 3 cubed. So when I replace it in my equation, I'm not changing the equation. I'm not making numbers disappear. I'm not doing that. All we've done is rewritten 27 with what we know it to be equivalent to, which is 3 cubed. Knowing that, now we have common bases. The base on my left side is 3, and the base on my right side is 3. That's what we wanted all along. So that is the true definition of showing the first case of changing bases when needed. Now from here, I see my base over here, b equals 3. And I see my base over here, b equals 3. Back to what we said, the property of equality of exponential equations. Because I have the same base, I also can equal my exponents. So that means everything up here at top as an exponent is going to be equal to each other. Our goal is to find the value of x. So I just need to bring these equations down and solve for x. X minus 2 equals 3 times 3x plus 1. All right. Notice I'm not worried about the big number 3's as the basis anymore. Once you have changed the basis to be the same, forget about them. Bring down your exponents and solve for your variable. Again, once you have changed to have the same base, bring down your exponents and solve for x. Our first step here will be to distribute this 3. I don't want to see parentheses. I want to distribute this 3 and invade everything inside the parentheses. So our next line we're writing is x minus 2 equals 9, 3 times 3, 9x plus positive 3. 3 times 3 is 9. 3 times 1 is 3. Let's go ahead and work this out together. Using inverse operations, I want to separate and have my numbers on one side and my variables on the other. So let's do that now. I always love to tackle the variables first. So I want to take x away from this side so that I can cancel it on the left side, and then I can subtract it from the right side. That cancels on the left. I know on the right side, I'm going to be left with 8x because 9x minus 1x equals 8. And only negative 2 on the left side. So we've canceled out the x. Now I need to do my numbers on one side. I need to move the 3 over to the left side. Because the 3 is being added, the inverse operation is subtraction. So I'm subtracting 3 from both sides. Now I have negative 5 equals 8x. Again, inverse operations are happening to get x by itself. We're undoing the equation so that the variable is alone and isolated. The last inverse operation, this says 8 times x if I'm reading it mathematically. That 8 is bothering the x, so the inverse of multiplication is division, and that is what we're going to divide by 8 on both sides to get the x by itself. So we get that x, the final answer, equals negative 5/8. Okay? Again, this is showing the first case of changing the base of an exponential equation. Let's look at the second case, which is using log in order to figure out the exponent or the value of whatever variable is given inside of a problem. So looking at example 2, we have 4 raised to the 3a equals 7. We want to get a all along by itself. But I notice this is a difference from number 1. I don't have an exponential on both sides. I can't change 7 to be 4 raised to the base of anything, at least not a whole number. So in this example, we're going to have to use our exponential inverse of logarithm in order to solve for the equation. The first thing to ask ourselves is the exponential part isolated? Yes, it is. Here's the exponential part here, 4 raised to the 3a. It is isolated. There's no plus or addition or multiplication on the outside, so we've got it alone by itself. The next step is for us to move into its inverse form, which is logarithm. So we start off by writing log. Our base is 4. Our argument is 7. And our exponent equals 3a. If you have a struggle with writing logarithms, rewriting between forms, please check out that video on Google Classroom. Again, our goal here is to get a alone by itself. Us changing to logarithm form, it just did half the work for us. Now I see on the right side, there is a 3a alone and isolated, but I don't want to know 3a, I want to know just a. So again, using inverse operations, because we know division is the opposite of multiplication, that's what we're going to do to both sides. Divide by 3 and cancel it on the right side. For us, that means a equals log base 4 of 7 divided by 3. And that's it. We have isolated our variable and got it alone A does in fact equal log base 4 of 7 divided by 3. If you want to go further and put this in your calculator to evaluate what is, in decimal form, the log base 4 of 7 divided by 3, you can do so as well. Number 1 required us to change bases from 27 to 3 cubed in order to use this property of equality of exponential functions. If I have the same base, all I have to do is bring down the exponents and solve for my variable. Whereas the second case was us looking at how to use logarithm in order to solve and find the variable in the exponent. Why do we use logarithm? Because there was no way we were going to be able to change 7 to a base of 4. I can't raise 4 to the power of any whole number and get 7. 4 to the first is 4. 4 squared is 16. 4 cubed is 64. So I can't get out 7. That's why logarithm form as an inverse helped us solve to get the exponent alone. Then we use inverse properties to divide by 3 and solve to isolate our variable. I hope this video has helped on solving with exponential equations, the two different cases of either changing your base or using logarithm as an inverse. See you later.